started recording. So moment generating function mxt, its short form is MGF. Okay, I hope you can hear me. If not, then you respond. Okay, that ma'am, I am not being able to hear you. So moment generating function mxt is given by expectation of e to the power t capital X. Now this capital X, as you have learnt earlier, is a random variable. Earlier in semester 1 we have come across normal variables. Capital X is a random variable, means with the normal frequency type variables a chance factor or a probability has been associated. For example, can you see the whiteboard? Can you see the whiteboard? Yes? Pinky, can you see the whiteboard?
नो मैम, मैम लिंक पर क्लिक करके जाना है क्या?
Whiteboard? Yes,
No,
I
ma'am.
have presented it. Now you check. Can you see it now?
No, ma'am. Ma'am,
Ma'am,
Jamboard.
we haven't downloaded Jamboard.
Can you see a whiteboard?
No, ma'am.
Okay.
मैम Jamboard डाउनलोड करने के लिए
No,
बोल
it's
रहे हैं,
not
इंस्टॉल
required
करना
for a Gmeet on over the mobile. It's required to be downloaded, but for laptops, it's not required. It is a normally available with the Google Meet option. So now can you see it?
Yes, ma'am.
Yes. So
Yes, ma'am.
so what is capital X?
Random variable.
Yes, it's a random variable. Suppose I tell you about the event, about the experiment that a coin has been tossed. So what are the possibilities for this event? H. What are the possibilities of this experiment? H and T. Now for H, I assign a variable x1, and for the event T, I assign 0 to the variable x. Now this 1 can happen when H appears, okay, and this 0 will, x will take up the value 0 when T appears, okay. So simple events H and T of the random experiment where one coin has been tossed, see, I have converted them into two numbers. H will be called 1 and T will be called 0, and these two numbers I have assigned to a variable x. Now this x variable will not take the value 1 all the time. It will take the value 1 only on such certain occasions where we will have the heads, and x will take the value 0 on the other occasions when the coin will be flipped and we get the tail. So suppose P is the probability of getting a head. P is the probability of getting a head. suppose P is the probability of getting a head. Let us write that. So let us write the probability of getting the head is small p. Then what is the probability of getting the tail? What is the probability of getting the tail? The probability of getting the tail should be probability of getting the tail should be 1 minus p, because it's the complementary event. So 1 minus p is sometimes called q, right? So that p plus q equals to 1. Okay, so that p plus q equals to 1. In this case, x is called a random variable. When should it have been a normal variable? It should have been a normal variable, that is a frequency type variable, if it would be taking up certain values and we will not be considering the probabilities attached to it. So that is called a simple variable. But in this case, x will take up the value 1 with probability small p and will take up the value 0 with probability 1 minus p or q. That is why x is called a random variable. Are you clear up to this? Are you clear up to this?
Yes, ma'am.
Yes. Now, what is expectation of x? Once I know a variable, the next question comes, what is the average of that variable? Average means, suppose I have heights of students in mathematics honors semester 2. Okay? But I need to know in most of the occasions what is the mean height of all the students, so that I can understand that what is the general structure of body line or body structure of the students of mathematics semester 2, because you know height and width depicts the general body structure, well-being of a person. Okay, so understanding the average is very important. Here also, after I have come across a random variable, the next question is, what is the average of that random variable? Now, you obviously understand this average will not be that simple as summing up all the values and dividing it by the total number of persons present or individuals present. Okay, because in that case, for a simple variable, finding out the average is all possible values that it can take, division by the number of persons or individuals on whom those values have been taken. But here, since probability is involved, so this average is given a different name called expectation and is referred to as capital E of the capital X variable. Random variable is usually termed as capital X, and the observed value of this X, that is, suppose X takes up the value 1 for a particular event, for a particular incidence of the coin tossing problem, then we can say small x equal to 1. But in general, when I don't know what has actually happened here, I termed it as capital X. So capital X we term for probabilities. We talk about capital X for theoretical type of distributions, and whenever it takes up a certain value, observed value, then we talk about small x. Okay, do not get confused. Wherever I am writing capital X, you have to write capital X, otherwise marks may be deducted. And wherever I will be writing small x, you have to write small x. otherwise marks will be deducted. So any realization, any observed value of capital X can be termed small x, otherwise you have to denote it by a capital X. Always remember, within expectation, within variance, always you have to write it as a capital X. Okay. So expectation of X, it is the average of the random variable X. It is given by, for a discrete random variable, it is given by summation X into fx. X.
Ma'am, small x mass point.
Yes, very good. That is probability mass function. Okay, this small effect is the probability mass function. These are the mass points. X is the mass point, and X can take up the values in the range specified by capital X. Okay, so we write it as this, the range of capital X, script X. Okay, so X can take up the values, belongs to, this sign is belongs to capital X or script X. And if capital X would have been a continuous random variable, then expectation of X would have been integration over the range of X, that is X belongs to script X, X times fx, X times fx into dx. Okay, that is the derivative. Okay, so if capital X is a discrete random variable, that is, it takes up isolated values within a range, then expectation of X takes up the summation formula. Whereas if capital X is a continuous random variable, then it takes up the integration formula. Examples of discrete random variables, like here, X takes up the value 1 or 0 for appearance of head or tail, and where can we get X as a continuous random variable? For example, if X takes up the heights of the different students in your class, then it can take the value between 4 to 6 with all possible decimal points in between, that is 4.2.6, 4.26, 4.59, 5.23. So all possible values in the range 4 to 6 it can take, and therefore capital X, if it is the height of a student of semester 2 of mathematics honors of AJC Bose College, completely specified, then capital X will be a continuous random variable, and it will take up, expectation of capital X will take up the integration formula. Understood, I hope. Now, based on this definition, if I am talking about MGF, you can see the whiteboard, right?
Yes, ma'am.
What is MGF? MGF is expectation of e to the power small t into capital X. What is small t, dear? Small t is any positive integer. Okay, any positive integer, whereas capital X, it is the random variable. Why do we take this form? Because this form, later on we will find out, this form helps us to find the different moments of the distribution of X. X has a distribution like 1 with probability P, 0 with probability 1 minus P, This is called the probability distribution of x. I think you have learned that with SB ma'am. So x takes up the value 1 with probability small p and 0 with probability 1 minus p. This is called the probability distribution of x. So in general we talk it about as the distribution of x. Okay. So x has a distribution of its own, and this distribution is like a curve. This distribution is like a curve. Okay. This is, say, the distribution of x. Okay. So for a continuous random variable, for a discrete random variable, x will take up only mass points, so it will only appear as a column diagram. Okay. So this is for continuous, the first one. The second one is for discrete random variables. Now these distributions have their
Ma'am,
moments. Yes, Pinky, tell me.
मैम e raised to tx के जगह पर मतलब कैसा ये रहेगा? e raised to x तो फॉर्म होता है ना, e raised to
No,
x.
I'll tell you about that form.
मतलब
Don't you worry
e
about it. Don't you worry. Try to understand the conception first. All the forms and algebraic manipulations, I'll go about it. Okay. But if you don't understand the basics,
okay ma'am.
it will be very difficult to do the sums. That's why I always give more importance to the basics. Okay. So what I was talking
Okay ma'am.
x, if it is a random variable, it must be having a distribution. Distribution means a probability distribution. These two figures tells the distribution of a continuous random variable, and the lower one tells me about the distribution of a discrete random variable. Okay. So for a continuous random variable, it looks like a curve. For a discrete random variable, these are straight lines, or these are called column diagram. And these distributions have their own moments. What is a moment? Moment, these are the mean, these are the standard deviation, skewness, kurtosis. That is how, what is the maximum length, what is the maximum height of this curve, or what is the maximum expanse of this curve. Okay, where are all the values situated in this curve? So these are some moments. Moments means, usually in layman term, moments are nothing but the first four moments are: number 1, mean; number 2, standard deviation; number 3, skewness. Skewness tells me whether the curve is symmetric or asymmetric; and number 4, kurtosis, that is how steep the curve is. Steep, you understand? STEEP, how steep the curve is. Okay, so these moments can be understood from this MGF. Okay, so MGF, that is why MGF's full form is moment generating function. So these moments can be understood from the function of MGF. So if x is a discrete random variable, then what will be this moments expression? And if x is a continuous random variable, then what will be this moments expression? That we will learn from today's class. So I'll once again go back to the classroom that we were teaching. I'm sharing this tab. Can you see it?
Yes, ma'am.
Yes. So mxt, that is the moment generating function, that equals expectation of e to the raised to the power of tx. And that can be written as similar to what we have learned just now. When there was only a capital X within expectation, we had written it as summation x into fx. But now within expectation, we have e to the power tx. Therefore, within summation, we will also write e to the power tx small fx. Okay? But here, since it is now an observed value of x, That is why we have written x as a small x, whereas within expectation we had written it as capital X. Okay, you remember. So e to the power tx into fx. Capital X is the discrete random variable, whereas small fx is the PMF of x. What is PMF? It is the probability mass function. I am not explaining it in details because ma'am has done already with you PMF and PDF. So capital X, discrete random variable, and small fx, then it's called the PMF or probability mass function of x. And it takes up the format or form of integration over the range of x e to the power tx fx dx, where x is the continuous random variable and now fx is called the PDF of x. What is fx? It is the probability density function of x. In the previous case, just for a small bit of information I'm telling you, when we have discrete random variables, we get only masses at the different columns. I just showed you two diagrams, one a column diagram for discrete random variable. So for that discrete random variable, at those columns occur at discontinuous spaces, right? And at that point of the column there is a rise. Again there is a space and again there is a rise. Space and rise. Space and the column rises. Correct? That is why at isolated points of x we get some masses. That is why it is called probability mass function. Probability mass function gives you those masses. Okay? And why for a continuous random variable we get a probability density function? Because you see, when we get a curve, the points are densed. Densed means near about one point there are so many points, innumerable points, uncountable points. We cannot count them actually. So it is called densed with points, and that is why it is called the probability density function for a continuous random variable. I think I have made you clear about the conception of expectation, random variable, discrete and continuous. Now t is a real constant. Usually it is a positive integer, but we have taken it to be a real number, which is a constant. Now let us expand this e to the power tx as a power series. This we have already done in class 11 and 12. E to the power 2, e to the power 3, e to the power x, e to the power minus x. These things, power series, we have done in class 11 and 12. So let us follow that. mxt is expectation e to the power tx. So within expectation, if I just expand e to the power tx, the power series that we get is 1 plus tx division by 1 factorial plus tx square by 2 factorial plus, it continues till tx to the power r by r factorial till infinity. And now if I distribute this expectation, so expectation has a very good property that it can be distributed over the pluses and minuses. Okay, expectation can be distributed over the pluses and minuses. So expectation of 1 is a constant, so it will remain 1. Okay, averaging 1, what do you get? 1, because you understand that very well, that if you want to average 1 for n individuals, then it is 1. 1 into n by n becomes 1. Now t is a constant, it will move out of the expectation. 1 factorial is a constant, it will move out of the expectation. So the second term will have only expectation of x. Similarly, the third term, the fourth term, everything will have within expectation the terms involving x, and the other terms being constants will move out of the expectation. The r plus 1th general term of the second line is t to the power r by r factorial expectation of x to the power r. Now this expectation of x, this is known as mu1 prime naught. Okay, I'll just show it again in the Jamboard. I hope you can see the Jamboard, right?
Yes, ma'am.
Yes. Now you must know this. Expectation of x to the power r. This is the rth order theoretical moments of a distribution. This is the raw moments about 0. You can simply call it mu. This is mu, okay? Mu r prime. Expectation of x to the power r is the rth order raw moment mu r prime. Okay, so the expression looks like this. So if I talk about r equals to 1, we will get mu 1 prime, and this is expectation of x. Expectation of x, and expectation of x is nothing but the mean of the distribution. This is given by mu. What is mu 2 prime? Mu 2 prime is expectation of x to the power 2. What is x to the power 2? It is expectation x minus x bar whole square x bar is nothing but expectation of x. I am writing expectation of x so that, or mu. Writing x bar here, you may get confused. That is why I am writing expectation of x minus mu whole square. But because of this, there has been an excess, so we cancel mu square from it. Okay. Yes. Here will be a plus. So expectation of x square equals expectation x minus mu whole square plus mu square. Why do we need this? Because this first term is nothing but the variance of x. Variance of x plus mu square. What is variance of x? Variance of x is nothing but SD square. What is variance of x? Variance of x is nothing but the standard deviation square. So S square plus mu square. So these two moments are very important for us, and we have learnt their expression. So for r equal to 1, expectation of x becomes the first moment, and that is the mean or average mu. And for r equal to 2, we get expectation of x square, which is nothing but the second moment, raw moment, and that can be expressed very easily as s square plus mu square, that is sd square plus mean square. So now look at this one. So you understand very well, only going through the book and only going through the LMS will not be enough for understanding the mathematical portions. Okay, you have to come to the class, otherwise all the crux of the teaching will be lost. You will not be able to understand everything on your own. Okay, you need to come to the class. Even though there is LMS, even though there is a book, you need to come to the class every day. And if you miss one of the classes, you need to contact your friends to understand what has happened in the class. Okay, that is why I'm trying my best to upload these videos in my YouTube channel. After this class, I'll try to post the channel link, and please see those videos, and you try to understand from there once again. Okay, if you have missed out something, or you need to go back and check what ma'am was talking about, you can see the video. It will be very much helpful to you. I don't want that you need to share it or something. I wanted that the students of my class gets to know about it. But it's a policy of the government, so we need to share it in the open platform. That is why I'm going to share it over the YouTube channel, so that any student, marginalized students who cannot afford to go to the tutors, can watch these videos and get some bit of help wherever they want. Okay, so you did not share the link to anybody. I won't ask it from you. Please don't share it, the links. It is open, anybody can watch it. You can do one thing, you can give a like there. As many as likes are there, the videos will be more rated and more students will be able to access it. So you need not share it anywhere. It will be visible by its own merit. Okay, if you really think these videos were helpful for understanding the class once you need them, then you go back and you just give it a like. Once you give it a like, the YouTube automatically will promote it. Okay, so you don't share it. So what I was talking about is expanding e to the power x as a power series is this. And the last expression that we have obtained is expectation x square, expectation x to the power r. And from the whiteboard we have just seen that is this expectation of x is nothing but, this expectation of x is nothing but the general mean. Expectation of x square is related with SD, and I have shown you the expression. So in general this can be written as expectation x equals to mu1 prime, expectation x square mu2 prime, expectation x to the power r mu r prime. This within bracket zeros you may give, you may not, because in general if you are calculating moments about 0, you can denote them as mu1 prime, mu2 prime and mu r prime. Okay. So the coefficient of t to the power r by r factorial in this mxt is the rth order raw moment about 0. You see, you check what is the coefficient of t to the power r by r factorial. You check in this last expression, it is mu r prime, and this mu r prime in mxt is the rth order raw moment. Now, if this mxt is differentiable, then we just do this differentiation. Even then also we can reach this mu r prime, because you can see from the above expression mxt has the term t to the power r factorial division by r factorial into mu r prime. Okay, so if I do a differentiation, first order differentiation, then the first term will vanish because it's a constant. If I do a second order differentiation, then the second term will vanish. If I do a third order differentiation, the third term will vanish. Similarly, if I do an rth order differentiation, the rth term will vanish, and what we will be left with is t to the power r. What we will be left with is mu r prime. Okay. So mxt, if it is differentiable, then also we can find the rth order raw moment by differentiating mxt r times. Now, what is the importance of this MGF function? This moment generating function, it is unique. What is the sense of this uniqueness? It is unique in the sense that it completely determines the distribution of a random variable. It completely tells you about the distribution. What is the meaning of that? Completely determines the distribution means it tells you about the mean, it tells you about the standard deviation, it tells you about the height, that is the symmetricity of the distribution and the pickedness of the distribution. So the full picture becomes clear to you about the distribution of the random variable capital X. That is why moment generating function is unique. Two distributions cannot have the same MGF. Okay, maybe the means can be same for the two distribution, but the SDs will not be same. Maybe the SDs are same, but the skewness will not be the same, or the kurtosis will not be the same. Okay, 4 parameters are needed to completely specify a distribution: the mean, the SD, the skewness and the kurtosis. So maybe 1 and 2 moments may be same for two distributions, but it is generally not true. Even if it is true for 1 or 2 moments, all the moments will never be the same for two distributions.